I'm going to present the article entitled Auto-Scaling in NFV using Tacker. The authors are William Salles, Emanuel Coutinho, and José Neumann de Souza, from Federal University of Ceará, Brazil. Nowadays, computer networks are composed of hardware appliances with specific functions, such as firewalls, load balancers, web proxies, and web servers. Generally, the implementation of these appliances is a difficult task because of its proprietary nature and the lack of specialized professionals to integrate and keep them. In these appliances, network functions (NF) are highly coupled to the underlying hardware, ensuring high performance and reliability at the cost of a low flexibility of network infrastructure. Thus, even a simple change of location of a middle box in the networks becomes a difficult and complex task. Thereby, network function virtualization (NFV) is a proposal to decoupling of the network functions from the underlying hardware, deploying them on commodity hardware. One of the greatest benefits obtained by NFV approach is scaling, which is the ability to dynamically extend or reduce resources allocated to the VNF as needed and at a runtime. Scaling may arise from the need of the scaling out the VNF to handle added load or scaling in to release unused resources. In this context, auto-scaling is ability of automatic scaling of VNF, and it provides better resource utilization and better service at a lower cost. Thus, it is possible quickly create a new instance of a specific VNF that is overloaded in order to split the workload. In the same way, it is possible to destroy instances that are idle. In this context, the aim of this work is to experience the auto-scaling functionality available in Tacker in order to verify the benefits achieved by solution. As secondary objectives, we will perform a review of the solutions that implement NFV manual management and orchestration architecture. Moreover, we will present the Tacker architecture. Tacker is integrated with OpenStack Horizon Service, so the VNF management is done through the dashboard. The VNF manager, highlighted in green, is responsible for managing the VNF instance lifecycle and can instantiate, update, query, resize, and destroy VNFs. The requirements for deploying and operating behavior of each VNF is represented by a template called VNF descriptor (VNFG), which is stored in a VNF catalog. The NFV manual architecture uses VNFG to create VNF instances and to manage their lifecycles. The resources of NFVI are assigned to a VNF based on the requirements stated in VNFG, in addition to considering specific requirements, restrictions, and policies which may overlap the VNFG. VNFM uses the Virtualization Deployment Unit (VDU) as an abstraction to describe the deployment and operational behavior of a VNF subset, or the entire VNF. Thus, it is possible to define the hardware and software requirements necessary for VNF deploying. The main function of the NFVO is to coordinate groups of VNF instances, resulting in network services that perform more complex functions. Moreover, it performs manage the lifecycle of network service instances, instantiate the manage of VNFMs, maintenance of information about the relationship between network service instance and VNF that compose it, configure the connections between VNFs, and dynamic management of configuration changes, such as resizing the capacity of network service. Scaling can be initiated in a number of ways, or by a manager who needs to increase the capacity of the VNF in advance due to a forecast, or by a management system that needs to maintain the Service Level Agreement (SLA). Auto-scaling is a cloud computing service feature that automatically adds or removes computing resources, depending upon actual usage. Autoscaling can automatically increase the VNF instances number during peak demand to maintain performance, and decrease capacity during idle periods to reduce costs. It helps ensure the correct VNF instances number available to handle the load. In this experiment, VNFs will be deployed and subjected to a high processing load, so that Tacker automatically creates new instances to distribute the workload. For the experiment, a scaling policy was defined to scale out the number of VNF instances when CPU or RAM memory usage reached 70% of total availability. The initial number of instances is 2, and it can vary up to the maximum limit of 3 and minimum limit of 1. CPU processing loads and RAM memory usage were easily retrieved by the Tacker monitoring framework in conjunction with Ceilometer. The environment used to carry out the experiment consists of one server and one workstation, interconnected by a switch. The table shows the CPU usage in instances 1, 2, and 3. At the beginning of the experiment, CPU usage of instance 1 was 10% and instance 2 was 16%. After the stress tests, CPU usage of instance 2 reached 70%, triggering alarm triggers for the Tacker monitoring framework, which initiated the instantiation of a new VNF. The figure shows the exact moment the NFV was performing the scaling out, represented by the pending scale out stage. After the new VNF instantiation, the load could be distributed between the 3 instances, causing a decrease in the CPU usage of instance 1 to 46% and instance 2 to 52%. Auto-scaling NFV provides better resource utilization and better service at a lower cost, and Tacker is one of the solutions that implements the NFV manual architecture and auto-scaling NFV. This work performed an experiment to present the use of the auto-scaling functionality in Tacker and OpenStack. As future work, we intend to design a larger experiment with more VNFs and collect metrics to improve performance. Furthermore, a strategy that can be used is to calculate how much the environment is elastic in a computational cloud environment by means of specific elastic metrics. Thank you for your attention.